Keeps changing. Okay, recording in progress, yay. All right, so, welcome everyone to, this joint session of MapTime Davis and Davis R Users Group. I'm excited to see you all here, because it's fun when there's more people in the room, but also because I just love R and spatial things. My name is Michelle Tobias. I work here at Data Lab. I'm a data scientist that works, almost exclusively with spatial data. And I'm one of the folks who helps make map time happen. We also have other folks in the room who help make map time happen. We call them our Map Time Davis Council, so wave council. Hey, thank you for your service. So this happens because it's a community thing, right? Like this happens because people take time to make this happen. It's not something that, we get a ton of funding for. It's really just people volunteering. So plug for helping out if you have the time and energy, but also just thank you for being here because that's also what makes map time happen is people coming to things. So today we have a workshop on intro to GIS and R. Elise Hellwig is our presenter and she needed to be remote today. So we got to connect to Zoom anyway to make the projector work. So I was like, hey, we'll just do it this way. So don't be confused. Your instructor is in a little box in the corner today, just because that's the way we needed to do it. Yeah, I think that's all you all need to know. Like I mentioned before, if you haven't signed in, please sign in, because that's how we know what's popular, what people are coming to, stuff like that. We're not going to put your email address on a list or anything and email you incessantly. It's just for ID purposes. But yeah, I think we're good. Did I miss anything, Elise, that we should mention before we get going?
No, I think we're good. Yeah, my name is, like Michelle said, Elise Hellwig. I'm also a data scientist here at the Data Lab and an enthusiastic participant at MapTime Davis, and I help run the Davis R Users Group. And I would highly encourage you, if you find yourself very excited about this stuff and but you need more help or just want to work with other people on our stuff, would highly encourage you to come to go to our website, sign up for the Davis R Users Group mailing list, and come to our sessions. So let's see. Okay, so first I'm going to let you all know that I'm assuming that you have RStudio and are already downloaded. If you do not, now is a great time to do that. Additionally, we're gonna need, and there are links. Let me step back a bit. All of the materials that I'll be using for this workshop are linked in the MapTime Davis event. So if you go to MapTime Davis website, go to this event, there'll be a link. And so everything you need, like, to do it and you can refer back to, there's actually more material there than we'll be able to cover. So yeah, so that's a great resource for you. But there's also links to where you can download R and RStudio. If you haven't done that, do that. Also, you will need to download the data, which is on Box, and you can use this link. And you can it'll take you to here, and you can hit download, and it should start downloading. Okay, awesome. So while y'all are doing this, I am going to pull up RStudio. So when you open RStudio, it should look something like this. Probably won't look exactly like this, but that's okay. But I want to talk a little bit about what are the differences and similarities between doing GIS using something like QGIS or ArcGIS and doing GIS in something like R. So Michelle, I think most recently Michelle and Oh my God, I'm so sorry. Who did the next steps in GIS?
Well, that was Lauren Mabe.
Babe, thank you. Thank you, babe. So most recently they have done GIS in QGIS workshops, and this is going to follow roughly Mabe's sort of the type of things that you did in the next steps, because there isn't really a way to do the intro to QGIS in R. It's a different program. But anyway, so QGIS and ArcGIS as well. These are desktop applications that have graphical user interfaces. So you're using point and click. When you want to accomplish something, you're doing that with like menus and tools. And generally speaking, everything that you do gets automatically visually displayed for you. And finally, it's QGIS and ArcGIS. These are GIS programs. That is their basically sole task. You can do sort of other things with them, but maybe it's easier to do that somewhere else. R is different. R is a programming language, and it's a more general tool. So you can do GIS in R, and we will be doing that, but it is not only something that you can use GIS. It's something that you can only do GIS in. And this has pros and cons. Pro is if only part of your sort of workflow is GIS related, chances are you can probably do your entire workflow in R, not just the GIS portions. Cons is it's a steeper learning curve. Instead of a graphical user interface, we're going to use a command line user interface. So like right here, we can do 4 plus 2, we get 6. All of everything we do, it's going to be stuff that is run in this command line. And instead of menus and tools, we're going to be using functions. The way function works, so let's say we want to take the square root of 4. There's a function called square root, sqrt. We do 4 and we get 2. Finally, R makes things more easily, in my opinion, reproducible because of something called a script. And that is, you can create a new script up here with R script, and this you can type in a list of R commands that you can save for later so you know exactly what you did, and you don't have to try to remember which tool you used or what options you used or what data set you used. You have a record of it here. But that does require you to write down the code that you use. So like right now, this 2 plus 4, this square root, this isn't going to get saved. When I close out R, that's going away. If we want to save things, we need to put them in a script. And we will be talking more about that in a little bit. So hopefully everyone has downloaded everything that they need. And to make everything a little bit easier, instead of just doing this in a sort of blank slate, we're going to create something called an R project. You don't have to do this, but I don't promise anything will work unless you do. And actually, I can't see, but can we have like a count of hands of if people haven't used R before? Is there anyone who hasn't used R before?
So we got one hand, maybe 2.
Okay.
Which is cool. You all stick around. You're gonna learn stuff.
Yes. So yeah, so great. So anyway, our projects are not required for R. It's not in R, it's in RStudio. But it helps you you know, keep things organized. And as Maeve said, in GIS, project organization is so important. This is something, project organization and documentation, super important, no matter what GIS program you're using, R, QGIS, ArcGIS, some other thing that I don't know about, Python, just like maps. Do you like to do things by hand? It's all, project organization is so important. So anyway, to make our lives easier, we are going to create a project directory. And we do this, you can click on this little thing right here. You can go to project, new project, and it should pop up. Okay, it's okay, here we go. New directory. We want a new project. And we are going to put this in, let's see, we're going to put, I'm going to put, you can put it wherever you want. I'm going to put it in teaching sandbox, and I'm going to call it intro GIS in R. I'm going to create project. And some things now have changed. You can see in the files area, we now have this weird R proj file. We're also going to create a folder, which we can do here. You can also do this in, you know, your file explorer or finder or whatever. But we're going to create a folder called data, and all of our data is going to go in this folder, and none of our data will go outside of this folder. And this is very important. And then actually, if we click on this, we're going to create another folder inside of the data folder called the raw folder. And this is the raw data, the data that we haven't done anything with yet. And we're never going to touch this data except to read it into R. We're never going to write over it because you never know when you might need to go back to your original data. As someone who has had to go back to my original data many, many times when I thought I would never need to, I can tell you this is a good practice. So now we have a folder, intro GIS in R, we have data, we have raw. Excellent. Now we need to get our data into that folder. So presumably your data got downloaded into the downloads folder. We can extract it using whatever sort of thing we want to. And then we are going to move this all into raw. And then now you can see we have all of our lovely data here.
How are you guys doing moving data? Everybody, okay? Okay.
Awesome. I know this doesn't seem like R, but this is so much actually more important than like remembering what code to write, is knowing where your data is. So I think hopefully you remember a couple minutes ago when I said that R is not a, oh, actually let's create a script for ourselves so we can keep track of things. R is not a GIS program. It's a computing language. And because of that, there is very little that you can do spatially in R without extensions, or what we call packages. And there are a whole bunch of different packages that you can use to do spatial data analysis in R. The primary one we are going to be using is Terra, because Terra does both raster and vector data. The other very popular one is SF, which only does vector data. But if you are a fan of the tidyverse and ggplot, it will play more nicely with that. So I don't want to do plotting with ggplot, and Terra sort of plays more nicely with baseplot, so we will be using Terra today. But I believe most, if not all, of the vector stuff we do is also in the workshop page as SF commands. So you can do basically all the same things for the most part. The commands just change. So like I said, we need packages, and these, because there are like thousands, tens of thousands of packages, when you install R, they're not installed. You have to specifically install them. And we can do that with a command called install packages. And you only have to do this once, but I'm going to keep it in my script because I want to remember that I have to do it on new computers and remember what the things are, what the command is. So we're going to do Terra, and then I'm going to use a neat little shortcut that is either Control Enter or Command Enter, depending on what operating system you're using. If you have your cursor on the line that says Install Packages Terra, and then you hit Control Enter or Command Enter, it automatically runs it in the console. So you don't have to do copy and paste nonsense between your script and the console, which is very irritating. Oh, we should save this. Let's see. Intro. GIS. Okay. And then, because I have worked through this before, I also know that we are going to want one more package. Something called R Natural Earth, which is basically just polygons that are nice for plotting, that are accurate enough, but don't take 5 million years to plot. And so we also want this one. Now, you might think as soon as you install packages, they should be ready for use. You would unfortunately be mistaken. In addition to installing the packages, we have to load the packages. Oh, also, comment. This hashtag, that means, tells R to ignore that line of code. Since I only need to run these once, I'm commenting them out, so that when I go to run this again, I don't accidentally reinstall everything. I mean, it wouldn't hurt, but it's more downloading that I don't need to do. So we need to load the Terra package and the Natural Earth package. We do that using a command, a function called library. So we do library, Terra, command enter. It may take a second, and then library, and our Natural Earth. And command enter. Okay. Excellent. We can tell if these have loaded successfully by using, looking for the help. So if we put a question mark and type in Terra and hit enter, the Terra package help comes up. That won't work if you haven't loaded Terra. There's a package called dplyr, which I have definitely installed, but haven't loaded it, so it doesn't come up.
I
Okay,
have a quick question.
yes.
When I loaded R Natural Earth, I got a warning package was built under R version 5.2 or something like that. I'm assuming since it's just a warning, it's not a big deal.
That is correct. That's something that I would ignore until you have problems. And then
Alright.
troubleshooting, I would say, oh, maybe I need to upgrade R.
Sounds good. I probably do need to upgrade my R.
So yeah. Yeah, it's one of those things. It's like, it's, 9 times out of 10, you're fine to run an older version of R, and then the 10th time, it's like, oh, that's why I'm getting an error. So, just, yeah. keep that in mind. And we won't need to use our natural earth too much. So I think you'll probably be fine. Okay.
Good.
So we have loaded our packages. We are ready to start doing GIS. And the first thing that we need when doing any spatial data work is we need data. Now, you can see we've got all sorts of data files in here. Actually, I lied. Even before we start doing GIS work, before we load in our data, we need a goal. This is actually critically overlooked oftentimes by myself. But what are we trying to do? So, San Francisco, did someone say something?
Oh, we're having trouble with the plugs. We fixed it.
Okay, great. So, San Francisco, very cool place. San Francisco, also prone to earthquakes. I personally do not want to die in an earthquake. And so I have decided that I'm going to make a map of all of the places where it is safe to be when I'm in an earthquake. This includes areas downhill of landslides I want to avoid, and areas that have very tall trees and are in soil liquefaction zones I also want to avoid, because they could fall on my head and I would prefer that not to happen. So that's our goal. Make a map of where we're not allowed to go if there's an earthquake in San Francisco. Okay, so now we do actually need data. And because we're going to be doing spatial data, the first function we're going to use to read in data from a spatial data is a function from the Terra package, and it's called vect. If we want to know about that function, we can do a question mark and type in vect. And this will give us a help file on vect. It's quite complicated. I'm not going to go into it. If you have questions on help files, I recommend you come to our Davis R users group. But the important thing is the first thing we need is a file name. So we have vect, and then we have a file name, and this includes the file path. So our starting location is intro GIS and R. And then from there, we're going to go to data. And then we're going to go to raw. And then we're going to read in the street center lines. So street center lines dot shp. This is a shapefile. Vect reads in shapefiles. It reads in a lot of other things too. But this is one of them. So if we hit Control Enter. Oh.
I'm missing an E.
Thank you.
Yeah.
Yeah, that's actually a very good point. If you see file does not exist when you're trying to load in data, it probably doesn't mean the file doesn't exist. It probably means you have the path to where the file is wrong, or you have a typo. So as you can see, we have an object here. It's of class spat vector. Its geometry is lines. It has some dimensions. It has a whole bunch of different variables. But it didn't pop up in our environment. And that's because we did not assign it to a variable name. If we want to save things so that we can use them in the future, we need to assign them variable names. And so in this case, we're going to assign this one streets.
Can I ask a really quick question?
Yeah, sure.
Super basic, but the class of this object is spat vector. Is that just like spatial? Like, I don't know.
Yes.
I'm very new to spatial data, so I'm more comfortable with R and I've never really used spatial data before, so.
Yes.
This
So-
is a new class.
Definitely. So And this is actually good to go over regardless of whether you are familiar with spatial data or not. Every type of object in R has a class. Some of the more common ones are integers, data frames, lists. However, those sort of basic data types don't really encompass the complexity of spatial data. And so Terra created its own class called a spat vector. That is a specific class that contains sort of like the normal data frame data, like, you know, your columns and rows, but also spatial data, like the projection, the where this actually all exists in space, the latitude, longitude points, stuff like that. Does that help?
Yes, thank you.
No problem. Okay. So we want to save this for later. We need to assign it to a vector. You can, the sort of classical R way to do this is a caret and a dash that equals, that sort of looks like an arrow. It's called the assignment arrow. Also, you can use an equals. They are equally correct, but the equal sign is one less character, so I tend to use that. But they're both equally valuable. Okay. So now we have our data. We can see, popped up in our environment, so that means we can use it later. And as you probably have noticed, we don't know what it looks like. Unfortunately, R does not automatically plot things for us. If we want things to be plotted, we have to tell R to plot them. We have to tell R to visualize them. Thankfully, that is not too hard to get somewhat of a visual on. We use the function plot. And the input is just the name of our variable that we've just created. And let's see, we can zoom. You can see, yes, these are streets. This is what we sort of thought it would look like, hopefully. And the streets that are roughly in the shape of San Francisco. Okay, excellent. For, at least for display purposes, it would also be good to have an outline of San Francisco. Thankfully, we have the shoreline shapefile. And we can just copy and paste this. And then instead of streets, do shore. Oh, shoreline.
With a capital S.
Thank you.
Sorry, that's my fault.
And if we run this, okay, shore popped up. And if we plot it, okay, well, it's definitely the shoreline of San Francisco, but it's also quite a bit of other things. So we may have to deal with that at some point, but we do technically have the shoreline of San Francisco.
You also have like the Farallon Islands and
Yes.
stuff like that. So.
Which is not great, but we will fix that later. You can also, another thing that you can tell for shore, if we just type in shore and hit enter, we can see this is a polygon. So it's not unlike our streets which were lines. These are polygons. So if we did something like fill equal blue and we plotted it. Oh, maybe not. Maybe color equal blue. Nope.
Might just be COL.
Oh, COL, you're right.
I know, I was just guessing. There you go.
There we go. So you can see it's all filled in. Okay. This is good. But we don't have any trees yet, and that's a big thing that we're worried about. Now, if we look in our files, you can see that the tree street map is not a shapefile. It's also not a GeoJSON file, which is, yeah.
I don't think there's one in there.
Oh. I don't know why I thought there was. Anyway, whatever.
I don't understand them, so I didn't put one in there.
Oh,
It's in the GitHub, but it's not in the file.
Okay, yeah, I don't think we'll need it.
okay. Yeah, we'll just use the, yeah, that's fine. This hazard zones. Okay. Okay, so the point is that our trees are CSVs, a CSV. And we can't read in a CSV with vect. It doesn't work. It's not a spatial data type. So we have to use a different function called creatively read.csv. And actually, I lied. First, we're going to read in the hazard zones. Let's see, what's the hazard zone? Seismic. Okay. 16 warnings. This may be an issue. What happens if we plot it? It's probably fine then.
It's just a warning.
Yeah,
It-
just a
it might-
warning.
It might be that, the geometry doesn't conform to the, definition that R uses for polygons.
Yeah.
And so it's throwing errors because there's like maybe multiple, like duplicate vertexes and things like that, which doesn't make it not readable. It just makes R be like, hey, this is not what I want. It's not, it's not perfect, but as long as it plots, it should be fine.
And we can go back and update the data later, but for now this will be fine. Yeah. So now if we want to see the top of any sort of tabular like object with rows and columns, of which HZ, our hazard zones, are one of them, we can use the function head. Oh, right. Well, that's cool. So we only have ID. That's fine. We will remediate that later. Once we learn how to read in CSVs. Okay. So we have tree map. I said there was a function called CSV. Read.csv. We have trees. Data frame, because that's the type of thing we're going to get out of read.csv. And then again, we want street, tree map, CSV. Okay. We run this. It's gonna take a second. There we go, because it has like 1 million or 200,000 observations. We can take a look at it. trees, DF. Great. So we have our x coordinate, our y coordinate, our latitude, and our longitude, which is what we care about. And then all of this other data that we may or may not care about. Okay. We have a data frame. If you want to know what class an object is, you can use the function class. Trees, yeah. It's a data frame. This is helpful, but it's still not a spatial data frame. It's not spatial in any way. If we plot it, I don't know what's going to happen, but it's not going to be a map of the trees. I can tell you that much. So in order to convert this to being not a data frame, in order to convert this to being a spat vector, we need to again use the vect function. We're going to do vect, and then trees df is the first input, and then the second input is going to be called geom, and that is just the name of the longitude and latitude columns, which in our case is longitude, latitude. And then the last argument is the coordinate reference system, which is, let's see, is lat long, but we're going to use the little EPSG shortcut, 326. And so then we
You spelled latitude wrong.
thank you. There we go. Now we have a trees spat vector. Excellent. And we can look at it using plot. And it'll take a second. And also that's clearly not right. Something
There's one tree that ended up in Alaska, and we don't know why. This is real data from the city of San Francisco, so it has, things happen to real data. We did not clean it, we just downloaded it.
Yep. So if we didn't know it was in Alaska, what we might want to do is download an outline of the United States and plot our trees on a map of the United States. And we can do that using the Our Natural Earth package. Our Natural Earth has a function called NE countries. And it just downloads country polygons. It's super useful if you want to plot something and you don't want to spend a lot of time looking for like a base map or something, since R doesn't really do like default base maps. So we are going to download the US, the country, NE countries, country equals, and I had to do a lot of searching for this. It's the full name, but all lowercase. Okay. And then because Natural Earth tries to be helpful to both people who use Terra and people who use SF, we have to specify what type of class we want. And we are going to use SV, which is short for spat vector. And so if we run this, what? Country. Perhaps first load the SF package. Okay. Apparently we need to load the SF package. So if you haven't,
Install that.
no. And then library SF. Okay. Let's try this again. Okay, apparently you need to load SF before this works, even though we don't care about having an SF. So we should add library SF to this, even though we're not technically using it in our code. R is weird like that. Okay, so now we can do plot USA. Now we have a nice plot of the USA. And base R has this useful thing, plot trees, add equals true. So we just plot it on top. And you can see, got some points somewhere in the middle of the ocean. This is not good. So this will lead us to our first real sort of GIS operation, which is cropping. We want to only have the trees that are like actually in San Francisco. But if you are a GIS person, as you know, in order to crop things, they have to have the same coordinate reference system. Incidentally, we do, let's see, we can get the coordinate reference system using CRS. So we have streets. Describe equals true. This just formats it nicely. We have streets. We have shore. We have HZ. And we have trees. So let's see. Okay, streets. That's lat long. WGS 84. This is lat long, also WGS 84. Hazards is WGS 84. Oh, they're all WGS 84. Okay, so technically we could have them all be WGS 84, but it can look kind of weird when you're plotting if you're using lat long. So we're actually going to project them all into California Albers, which is a sort of nicer for California plotting sort of looking projection. And very creatively, the function that we do this is project. So if we want streets, and we do project streets, and then EPSG 3310, I believe, is the EPSG for California Albers. And we can check, did it work? Coordinate reference system, California Albers. Excellent. Now, if we had a lot of these to do. I mean, 4 is kind of a lot. There are ways of automating this. So you use like 1 or 2 lines of code that will, convert all of them. I'm not going to go into that today because we have so much to cover, but come talk to me later if you are interested in automating your GIS workflow. So we can copy and paste this and do Shore CA. A nice thing about project is instead of using the EPSG code, you can also just use a object that has the right CRS. So we know Street CA has the right CRS, so we can use that to reproject Shore CA. And if we check again, this has, yes, California Albers. We are good.
Is there a way to find these EPSGs in like a help file on R that?
I don't know. There might be.
Google's probably your best answer, Alex says.
There's a website called epsg.io, and it's really helpful for looking it up. You can get it in R, but it's easier to just go to a website.
Okay, perfect, thank you.
And the more you do this, the more you will have them memorized. Like in my head, I know California Albers and I know Lalong. So you'll get used to the ones that you need and you'll remember them. They're good for tattoos, by the way.
I also vote
So-
that's one that's already bringing the right one in.
Thank you.
Okay. Let's see. We'll do hazard and trees. Run this and run this. Okay, great. So now everything is in a projected state, which is better for cropping and processing anyway. And they're all in the same one, which is key. Now, we really only need the what's it called? We really only need the trees where we have the shore, where we have the shoreline or the streets. We could also use the streets to crop. So actually maybe we'll use the streets, but the function that we're going to want to use is, I believe, called crop. Oh, wait. Oh yeah, trees is good. So I believe the function is called crop, but we can check to make sure that's what we want. Cut out a geographic subset. Yes. Yeah. This is correct. Okay. So let's see. So streets we're going to use as our base. And to make sure we're getting like getting everything, we are going to use not just the streets object, but an extent box that's around the streets object. And we can do that using the ext function. So it basically just gets a bounding box around it so we don't get any weird cropping behavior. So, so we want, let's see, shore we need to crop. Shore. We're gonna crop, oh wait, no, first we want street. XT of streets. So now if we plot this, we want to make sure it's a box. We have a box. The plotting can get tedious, but that's the only way you know what your stuff looks like, because R doesn't automatically display it. Okay, so we want to crop the shore. And we want to crop the trees. So now, if we plot shore CA, and we plot trees CA, and we're actually going to, for some reason, PCH is the argument for what type of point you want. So if we zoom in, we can see all of these little tree points. And you can see they go along the streets primarily. Question?
I wasn't paying attention. What PCH number did you use?
I used PCH number period.
Oh, okay.
I think it's the smallest one.
Okay. Yeah, I always use 19 and it's big.
Oh, 19. Let's see. Let's see what 19 does. Oh.
Yeah, it's way too, that's just in my head.
Oh, yeah. Yeah.
The period way
much-
better. I didn't know that existed.
Yeah. It's very handy when you're plotting like 20,000 different points. Okay. So we got them all together. This is excellent. Now, we are going to go on what I like to call a function interlude. This is when I teach you how to write a function in R, because we're going to be doing a lot of plotting, and we're going to be plotting the same things over and over and over again. And I really don't want to have to type out all 5 lines of code over and over and over again. And so we are going to write a function to do it for us. The way you write a function in R, actually, here's another shortcut for you. Command or Control Shift R, it'll create a section label. We do function interlude. And if you pull up right here, it has the sections on your outline. Okay, function interlude. How you write a function. First, we need to name our function. I am going to call it plot trees because that is what I want to do. Then we need an equals sign or an assignment arrow, and then we need the function or the keyword function. And then inside the function, we need to put placeholders for what we want the inputs to be. So in this case, what I want to plot is I want to plot the trees on top, and I want to plot either the streets or the shoreline or the hazard zones on the bottom. So we're going to do geom top. And then the next one is going to be geom bottom. And then finally, I want to make it easy to give this some background color. And so I am going to have one more argument called polycolor. It's the color of the polygon. and I'm going to give it a default color. Because I don't want to have to type in light blue every time, but I want the default background color to be light blue. Oh, except I spelled it wrong. There we go, light blue. Okay. Actually, let's do this so we can see everything. Okay, and then close parentheses. That is the definition of the inputs for our function. And then to define the body of our function, we're going to open and close squiggly brackets. And then everything that goes in here is going to be our function. First, we want a title. So I'm going to do plot title. And we're going to say street trees in San Francisco. Then we want to plot our bottom. And this is going to be, we're going to use the plot function. And then the input is going to be geom bottom. Color is going to be poly color, which by default is light blue, but we could change it if we want. And then we're going to put axes equals false, so we don't have unnecessary lines on our function. Okay, that's the bottom plot. We generally, when you're doing R plotting, you generally plot, or for base plot at least, you plot from bottom to top. It's like a layer cake. Then we're going to plot the top. The top is just going to be plot geom top, add equals true, because we want to add it to the geom bottom that we just plotted. And then I'm going to add, oh, I'm sorry, there's one more thing I forgot to do here, up top. Comma, and I'm going to add 3 dots here. And I understand that that's very confusing. What does that mean? What it means is put any arguments after polycolor, put them wherever you find 3 dots. And we're going to put them in here, which what this will allow us to do is to give formatting to this without having to predefine what that formatting will be. It's totally fine if you don't understand it. I'm just going to tell you that it'll work. And if it doesn't, we can troubleshoot it. So now we've got this function that we've defined. If we hit enter or control enter, we run the function and you can see now we have a function plot trees. So that means we can now use that function. If we do plot, let's see, let's move this over a little bit. Plot trees. The first one is going to be trees CA. Second one we'll do the shore CA. Color is going to be dark green, and PCH is going to equal period. If we run this,
Awesome.
so now we don't have to type in all of that code. We can just use our plot trees function. Did everyone get this picture?
Yeah.
Mine's just on each one.
Yeah, so I think talk to your neighbor, if your neighbor got it to work. If anyone's really stuck, let us know and Alex and I can come around and try to troubleshoot. But we'll give it a minute or so and see if we can figure out what happened on folks' computers.
This is the hardest thing, just so you know. If you can get this, you can get everything else.
Maybe Elise, can you put the screen up so they can see what your function looks like?
Yes.
No, I haven't done the class yet.
Elise, I gotta say, the three dots thing, it's, I didn't know about it, and it's awesome.
Yeah.
I've been writing some crazy functions and with so many
Arguments, yeah.
arguments. Yeah, I always learn something when you're here, Elise, this is awesome.
I'm so glad.
These changes to it and now.
Oh, yeah. Can we just plot the trees by themselves so they show up and just plot trees?
It's almost plotting functions.
So fun. This is so much for all new time, so excited.
And Ron, I start from the top and like where you love, because it seems like your trees are probably the problem. Make sure that the trees got resilience. Make sure you didn't skip a line in. It's weird that it's not throwing an error. But that counts sometimes.
And you go there.
Yeah.
I guess you're in the past, right? Or you went into fly.
I'm looking.
So, yeah, so you define the.
Oh, wow.
Yeah.
Make sure it did what I
Everything else,
wanted.
yes,
Yeah, so yeah, I think that was.
Cool. You figured it out.
And then you run.
Yeah.
run all the
Okay, so this is,
different-
that's good to know. So someone that's in there for the process, and probably did something that went a little bit awry. Can't work from home. Like that's like. They just. So I plot your tree, see it now and just. See. I like this, does it,
Should-
does it work?
Yeah.
Papers.
When you plot, oh, so when you plot your trees, you're plotting your shoreline instead. So that means somewhere in here, let's. That's the error right there. So I'm gonna switch that. But now I know it's right. This is super easy, like, to do when you're copying or pasting, you put it to change the result, you do it all the journal articles, easy math. Easy fix.
I do everything else and then I gotta like go over. I don't
Oh.
have to treat that anymore, so.
It's Yeah, so now, yeah, so then there's one other step in the workshop where we did the drawing and then that's.
Like that's.
The trees are turned out.
I was like trying to.
Oh, I did think.
Yeah, how do you?
There you go.
But now I have.
Yeah.
So why is?
There's just in the adding those through. So yeah, why we're sort of like then your trees are gonna do adding those trees so that they, it doesn't turn out the other.
Yeah.
So this is what I would like to like, so I think you're back on. So now try your function and see if your function works for plotting.
What is this?
Yeah.
Yeah.
It's just like a base plot.
How are we doing? Are thumbs up on the function now? It seemed like the theme of the room was like missing, changing the variable, which is really easy to do when you're copying and pasting. But easy fix.
Great.
So we good to move on, guys? Okay, let's give one more minute and then we'll, I think there's a couple
And-
folks that need another minute.
For sure. Just I want to tell you, I think for better or for worse, I find that writing functions tends to be a bit of an intermediate R level experience. So congratulations, you've all graduated to intermediate R.
While we're waiting, I'm curious about this like section that we created, Elise, that you called
Yes.
function interlude, like. Now moving forward is a best practice. This is a fun little trick for me. I've never used the, section outline before. So now is it, would you like recommend starting another one? Now that we finished this function, just keep yourselves organized, or how do you use this?
Yes. So, if you look in on the online thing, I've actually put a whole bunch of different sections in.
Okay.
I just presentation mode happens and I forget. So like, for example, is it okay for people if I move off of the function definition?
Yeah.
Okay. So like, for instance, I would probably put here like setup,
Mm.
and then here I would put nope. Read in data.
How are you adding these sections? Sorry.
Oh yeah, sure. Command or control shift and then R. And then here I might put crop or projecting. And then
Cool.
here I would put cropping.
Thanks, it's super useful. I always end up with these like long scripts and then have to scroll through, so this is really nifty. Yeah.
And then we can see, oh yeah, and you can jump to them as well.
So cool.
You can also collapse them with the little arrow on the side, so if you don't wanna see like your functions, for example, you can collapse that, it makes it
Yeah.
shorter.
It's like our markdown, but like
Yeah.
sleeker. Yeah.
Yes.
Cool.
Yeah, so I code almost exclusively in R Markdown. I like never use scripts. So this is helpful knowing you can put sections in.
Yeah,
Yes.
that's awesome.
Cool.
Noted, my plot title isn't coming up.
Oh yes, I forgot that again, presentation brain always moving forward faster than the rest of me can catch up. So the plot title, I forgot that we actually do need to put that into one of our arguments. For reasons that I don't understand, the argument where you specify a plot title is called main.
I do
And
this all.
so I added main and then set it equal to plot title in my first plot argument or first plot function, and then redefined my function and then reran it, and then we get the plot with the actual title.
Sweet.
I literally do this all the time with the wrong parameter. It doesn't make sense.
Yes. Okay, so cool. Now, like I said before, we care about trees not falling on our heads. But we really only care about that in areas where the ground is likely to turn to mush. And there are two different types of hazard zones in our lovely hazard zone area, but you wouldn't know from the data that we currently have. If we look at HCCA, we do head of that. We just have ID numbers, which is not ideal. But thankfully, we have more data. And let's give this a title, formatting hazard data. So if we go back to our files, we can see we have seismic hazard zones, we have the shapefile, but we also have seismic hazard zones data. So if we want some more information, we can read in that data again using read.csv. So hazard zone data equals read. Data. Oh, except we need these. And we read this in. And we do. Ah. Now we have GeoID and we have zone type. This is very good. This is what we want. Now it looks like in this data there is some duplication. And I have good news for you, which is that there is a function that will deduplicate your data in R. And that function is called, unsurprisingly, unique. So we have, I don't want to, the data equals see data. We run this, and then we run. Why are there still two? Oh, because we have two types. Okay, excellent. Okay, great. So now we have two data sets. We have one that is spatial, but doesn't have any columns in it. And we have one that has columns, but is not spatial. And so how do we solve this problem? We solve it with a function called merge. And merge is the heavyweight champion of combining data sets. If you are familiar with SQL, this does the equivalent. It does the equivalent of inner, outer, left, right, all of the joins in one function. So we're going to say, okay, HC California is going to equal merge. And this is where it gets tricky. Because depending on what the first argument is, will depend on what the output is. So if your first argument is a spat vector, then the output will be a spat vector, which is what we want. If your first argument is a data frame, your output will be a data frame, which is not what we want. So we want to make sure that our first output is our spat vector, which is HZCA. And then our next input is what we're merging with it, HC data. And then we tell the merge, the function or the argument that we use to tell it what column to combine these data using is the by argument. And we want to do by GeoID. Okay, great. Control enter. Oh, okay. Let me, okay.
HPCA is just ID.
Ah, it's ID. Okay, even better. Now we get to show more functionality. Okay, so by, if they have different columns, that's okay. We can use by dot x equals ID and by dot y equals GeoID. No symbol named by dot x? What? Okay.
Should have it.
Let's just try and see if it works. Okay, it did. It just was confused. Okay, so now we have HCCA. It's a spat vector of polygons. And, but we also have all of the columns that we need. And we can check to make sure that we have all of the columns that we need by plotting it using an argument that we haven't used yet, which is the second argument. So if we do plot HZCA, and then if the second argument we put zone type in, and then main, we can do CSF hazard zones. We zoom in. It's hard to see, but you can see that the shoot. Where did it go? Aha. Here we go. It's hard to see, but you can see that most of this is the liquid hazard, liquefaction or whatever it is called, hazard. Liquidation, and then the ones up here in where the hills are basically are the what's it called? The landslide hazard is. Which makes sense, you know, you don't see a lot of landslides on flat ground. Okay. Now we are ready to figure out what's going on with the trees. So we really only care about trees in our liquid hazard zone. What did they call that? Liquefaction hazard zone. So what this means is we need to do some filtering. We need only the hazard zones that are liquefaction, and we need only the trees that are very big. Now, unfortunately, they don't tell you how big the trees are height-wise, but if we look at, we can use this view command called view. We do trees, df. It lets us look at sort of in a better, nicer formatted sort of way the various arguments or the various columns that we have. So I don't much care about species because you can have, you know, tiny redwoods and very large other trees. Plant type is all trees. Don't care so much about that. DBH. If we have any tree people out here, you know that DBH means diameter at breast height. So that's how big the tree is around at about your chest, or 4 feet, basically. So this, we don't exactly know what this is. You know, it doesn't exactly correlate to height, but like, you know, if it's a 3-foot diameter tree, probably not big of an issue. 17-foot diameter tree, we definitely want to be staying away from. So I'm going to say I don't want to get hit in the head by anything bigger than 4 feet in diameter. I mean, maybe I would go so far as to say 3, but just so we're not still working with like infinite freaking points here. Let's go bigger than 4 foot diameter. So, okay. Let's do another section. We're going to do filtering. So we're going to filter Filter trees, so trees. CA. And if you haven't done R before, this is gonna look real weird. If you have, then then this will look less weird. Actually, we're gonna do this in 2 steps. We also want to know, because this is city data, you can get some pretty wild things going on with city data. So we're actually going to see what is the sort of summary of the data of this DBH data. So, what are the quartiles? So we can do that with the function called summary. And we want trees, CA, and we only want the DBH column. And so we do $DBH. We run that. Okay. Well, first of all, we have a lot of missing data, which we can't do very much about. For those of you who aren't familiar, NA means missing. We have a lot that are 0. That's fine. We don't care about 0 diameter, 0 foot diameter trees. We also have some that are maybe also not right on the high end. I'm pretty sure, in fact, I know the largest tree in existence, the tule tree in Mexico, has a diameter of 384 feet. So it is literally not possible for any of the trees in San Francisco to have a diameter of greater than 384 feet. So we are going to assume that any tree with a diameter of greater than 384 feet is in fact nonsense, and we're going to exclude it. We are also going to exclude any tree that has a diameter of less than 4 feet because we're not too concerned about it falling on us. And then we also don't want any of the missing data. And we are going to do this using logical statements. So we want to know if something is big. That is what we are going to call our variable that tells us if a tree is big. First, we want it to not be, not in our language is exclamation point. It's not going to be NA. That's the first thing we want. And ampersand, we want it to be greater than 4. And we want it to be less than 384. So now oh boy. Oh, it's just complaining about this. Okay. Now, this is basically just a vector of truths and falses, which may not seem very useful, but we can use it to filter our lovely tree data. So we're going to say, okay, trees big equals trees CA is big. Okay. Now, so let's see. We can see how many rows are in a tabular data form using the nrow function. So nrow trees CA is a lot. And end row trees big is less, but still maybe more than I wanted.
Could you take a second to explain the bracket, like how the bracket's working in
Yes.
in the big trees?
Yes. Okay. Okay. So, oh, this also should be, sorry. This should be like this. Okay. Brackets are the base R way of filtering. When you want to filter something, the first element of the brackets is the row filtering. The second element is the column filtering. If we wanted just the first row of trees.ca or _ca, we could do this. And this would give us just the first row. One dimension, 16, one row, 16 columns. However, we want only the places where this is true. And so we need a vector the same length of this that is trues and falses, and our no's only take the rows that have trues. I, very much like NASA, have made a units error. Which is that I forgot that the DBH was in inches and not feet. And so I said that we wanted everything that was more than 300 or more than 4 inches. We want what's more than 4 feet, which is in fact 48 inches. So that's why there were so many more trees than I expected. This is actually a key thing in R. Number one thing you can do for your troubleshooting is set expectation of what you think the answer should be, and then check to make sure that the answer is what you think it should be. Because you will note, I didn't get an error. It still did the filtering for me. I just got way more trees than I wanted to. Okay.
Since it's in inches, should we also update the
No,
nonsense?
that one is actually right. It is 384 inches. 384 feet would be a really large tree. I mean, 384 inches is still a really big tree, but I did actually look that one up. So I did get the number right. Okay. So now we have trees big, and if we look at the end row, this should be significantly less. Ah, yes, 1,700 trees. This is a much more reasonable number of trees to avoid. Still a lot, but they tend to be clumped together. So we've filtered our trees. Now we need to filter our hazard zones, which will be thankfully much easier because the hazard zone data is actually cleaner than the trees data. But we can still take a look at our summary. Filter. So summary, please. Oh no, HCCA zone type. Oh, that's not very helpful. Ah, what about this? Table. This will be more helpful. Yes.
I'm assuming you want table because it's categorical.
Yes, categorical. I thought sometimes summary will give you the values. Maybe only for, you know what, only for factors. Which we're not going to talk about, so. But yeah, table is very useful when dealing with categorical data. And actually, we can say exclude false. we wanna, this will, exclude equals false means asks, should we exclude NAs? Which there aren't any, but if there were, it would pop up. Okay. So, is liquid is going to just be hazard zone $sign zone type equals, and then I'm just going to copy and paste liquefaction so I don't have to worry about spelling. And then we're going to do the same thing we did here. Liquid equals CCA is liquid. And since we want to filter by the rows, we're putting this is liquid in the first element and we're leaving the second one blank because we just want all the columns. And now we look, let's see, n row HCCA is 165, but n row liquid is 67, which is the number of liquefaction zones that there were. So that checks out. How are people doing on the filtering? Good.
In an effort to reduce variables in my environment, because I have a problem with that, could we just, the is big equals the, and the ands, I can't remember what it's called, the logic. Could we just
Yes,
insert the
you
logic
could.
directly into the subset?
Yes, you could do this.
I think it's easier to read like this, but.
This is the same. But yes, I find this way easier to read. And also this is easier to troubleshoot if things go wrong.
So true.
Break it up into multiple pieces. Okay. So now we've got these big trees. And just to make sure that we actually have filtered them to a reasonable amount, we're going to plot them. And we're going to plot them on top of, instead of our shoreline, we're going to plot them on top of our liquefaction zones. So we're going to do plot trees. And then our top geometry is going to be trees big. And our bottom geometry is going to be liquid. And our, let's see, color is going to be dark green, and our other thing is going to be just a dot. Oh. Well, that's interesting. Oh, invalid color name. How is it an invalid color name? Oh, this. Forgot to put PCH. There we go. Okay, so now you can see visually the places where the trees overlap with the hazard zones. And actually, maybe this would be better for 19.
Oh,
Oh,
he's not have to have the quotes. It's literally plotting 19 as a character.
so yeah. So now we can see a little bit clearer where the plots are. So this is great as a map, but it doesn't tell us exactly where we can't go. And specifically, it doesn't tell us the streets we can't go on. So we need to do some more geoprocessing. The first thing we need is we need to know, okay, what are the trees that actually overlap with these liquefaction zones? And we can use, I think in QGIS it's called clip, but here it's called intersect. And so we're going to do some geoprocessing. And we're going to say, okay, trees, liquid is going to be intersect. Trees goes first because that's what we want to come out. And then the area that we want only trees from is going to be liquid. Oh. There we go. If you see a warning message, different CRS, even though that is a warning, you should consider it an error. Because if you have different CRS, if you have a different coordinate reference system, your answers are going to be wrong. Okay. So now we've done that, we can do plot trees again, but instead of trees big, we're gonna have trees liquid. And actually, I think is 16 smaller? We'll see. Yes. No, 16 is bigger. 19 is smaller. Okay. So now let's inspect. Did it actually work? Yeah. Yeah, it looks like it worked. Most of the trees are gone except for a few that are, you know, in these blue areas. Okay, this is great. So, last thing we need to do is we want to know, okay, what streets can we not walk on? What areas of what streets can we not walk on? If we want to avoid having our noggins bonked by some trees during a earthquake. And that is going to take 2 steps. First of all, we don't just want to avoid a tree. We want to also avoid the area around the tree. Now, ideally, and there's probably, well, I know there is a way to do this. If you knew the heights of the trees, you could, you know, do a buffer around each tree at its height. It would be a little bit more complicated, but definitely doable. We don't have the heights of the trees. So we are in fact going to just do a set buffer of 100 feet. And assume that probably most of the trees aren't 100 feet tall and call it good. So we need to get our buffer of 100 feet. And then we need to overlay that buffer with our streets to tell us which areas we should not walk in. I realize we're not going to get to the bit about the landslides, which is unfortunate because that's actually where we get to do raster stuff. But it is, I think there's a precedent for not doing raster stuff in these types of things. And all the information is on the internet. So you will be able to work through that on your own. And come talk to me at Davis, our users group, if you have questions. Or at Maptime Davis. Okay. So then we're going to overlay. After we do the buffer, we're going to overlay it with the street trees, or with the street lines. Okay, so we want to do a buffer, which I have forgotten what the name of that is. It might just be buffer. Yes. Okay. I guessed correctly. Okay, so trees 100 is going to equal buffer trees liquid and then the width equals, well, we want 100 feet, but I believe the units of this are not 100 feet. Yes. Are not in feet. So let's see. Okay, this is going unit. Okay, so this point, this CRS, if you don't do describe equals true, it prints out a whole lot of nonsense. But at the end it has length unit and it says meter. And so we know that the units are meters that we need to use. So we can, I'm going to say 30 meters is close enough to, or 33 meters is close enough to 100 feet. And so now we have our buffer. And we can plot this again. And we're going to say the color is going to be dark red this time. Tree is 100. Oh, they're just very, very tiny.
You
Oh,
could
well.
set border equals red too, and be a little more visible.
Oh, yeah. There we go. They're still going to be real tiny. Yeah, you'll have to look on your own screens. But yeah, they're there. Let's make it 200. 200 feet, just to be safe and to make this a little bit more interesting to look at. There we go. Okay, so these are all the areas we need to avoid. Thankfully, not very much. You know, just maybe, you know, stay away from some of the Embarcadero. Okay. So, just a second. So the next thing we are going to need to do, we have the trees. Now we need to overlay them with the streets. And to do the overlay, we can do a couple of things. First, as you can see if we zoom in, there's a lot of overlapping little dots. We don't actually want those. We just want, you know, one clean polygon of danger. And so we can fix that by using a function called aggregate. And if we, let's see, we're gonna call this danger zone equals aggregate trees 100. And as you can see, every time I do something, I am plotting it just to make sure it does what I think should happen. Let's see. We zoom in. We can see now there's no overlapping, so we're going to get a better sort of plot result. And then finally, we need to do a spatial relationship. We need a way to tell our what are the areas of the streets that we want to flag as being dangerous? And we can do that using a function called isRelated. And like our logical statements earlier, this is going to create a vector of trues and falses, whether or not these things overlap. So first, we want our streets. So is related. First argument is the streets. And the second argument is going to be danger zone. And we want them to be considered to be related if they intersect. Now this is different than the intersect we did earlier, because the intersect we did earlier is like an inner join. It's saying only give me the trees that are inside this polygon. In this case, we want all of the streets. We just want to know which streets are in the danger zone. And so if we run this, intersects. There we go. There we go. Okay. So if we look at this, we do head, you can see it's these trues and falses. And we are going to use that to add a column to our streets data set. And we can do that using, previously we used the $ to extract a single column. Now we're going to use the $ to define a column. So we have streets CA $ in danger equals in danger zone. And now, if we do head, head this, we can see we have all of our streets and we have in danger false, and then some of the time it will be true. Okay. Now, this is great, but true and false are not very evocative labels. So we are going to define one more column that will be more clear as to what we mean by, by these categories. And again, we're going to use the same $ situation, but this time we're going to call it status. And we're going to use one of my favorite functions in R, if else. And this basically takes an input, in this case, our column. And if this is true, if we are in danger, it is going to return danger. Avoid. And if it's false, it's going to say have a nice walk. Smiley face. And so now we have a status. that we can use to finally plot where we think we should go during an earthquake. So let's see. Your title, we're gonna call this street safety status under seismic hazards. And then we're going to do plot streets CA status, because that's the column that we created. And then the colors are going to be, we're going to have two colors. They're going to be this random red color that I found on the internet. And gray 50. Title and axes equals false. Okay. Let's try this. Whoa, I forgot to run danger control. Zoom. There we go.
Yay.
5 minutes to spare. Not too
I was
bad.
gonna say, I think it's probably time for any questions that we've got and to wrap up because we've got another workshop coming in right now, so. So I guess first let's thank Elise for this wonderful workshop. And then we'll have time for like maybe one or two questions, depending on how long they are, before we gotta wrap up because the next thing's coming in.
I had a question about the buffering that we did. What
Yes.
exactly, can you just review what exactly the purpose of that was versus just plotting the actual points of the trees?
So the idea is that we want to avoid not just the tree itself, but areas around the trees, because when trees fall over, if a tree is 50 feet tall, you want to be at least 50 feet away from the tree or you could get hit. So the buffer allowed us to say, okay, we want to be at least like 100 or 200 feet away from these trees to avoid getting our heads bonked.
Okay. It's hard to see on the plot because the points are plotted like so large, but technically a point has no area.
Yes.
And so if you were to do the buffer of like 1,000, like you would see that it's like much, it like turns a point into an area.
Okay.
But it's hard to see because the buffer itself is fairly small.
Yeah, thanks. Cool. Well, thank you all for coming. This has been super fun. Join us, I think, next week. Let me look at the schedule real quick. We kind of did some shaping up of things. So next week, we would normally have a work session, but we're gonna be doing humanitarian OpenStreetMap work. So we're gonna be working on a group project to add data for a humanitarian disaster situation that needs help. We don't know what that is, I don't think yet, because disasters happen without warning a lot of times. But join us next week. We'll learn about OpenStreetMap and how to add data and do it for a humanitarian purpose. All right, you're welcome to stay for the next thing, but we're gonna pack up nap time.
Great. Have a great day, everybody.
Awesome.